Swayam Prabha. Digital India. Educated India.
Welcome to lecture 21 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Detection and Solutions to Multicollinearity. In the last lecture, we discussed the problem of multicollinearity, exact multicollinearity as well as near multicollinearity. We observed that the properties of OLS estimator get deteriorated in the presence of multicollinearity. In fact, if the multicollinearity is exact, you will not be able to obtain the OLS estimators. And in case of near multicollinearity, of course, you can obtain the OLS estimator, but the OLS estimators have very large variance. So, the estimators are not very efficient. Another problem is that the estimators are very sensitive to small changes in data. So, the estimators are not very robust. Then because of large variance, if you test the significance of the regression coefficient, then often the null hypothesis that the coefficient is insignificant gets accepted. So, this is something strange. On one hand, we get large regression parameters in magnitude. On the other hand, the null hypothesis that the coefficient is insignificant gets accepted. Further, because of the large variance, the confidence intervals are also very wide, which is not something which we like. So, now in this lecture, I will consider different measures of multicollinearity, which you can use for the detection of multicollinearity. Then we will also consider different solutions of the multicollinearity problem. If your model has multicollinearity, then how can you estimate the parameters? So, we will discuss different estimation procedures for the regression parameters. So, first we consider the detection of multicollinearity. The first measure is condition number and condition index. So, we define the condition number as say kappa x equal to lambda 1 upon lambda k to the power half. Here lambda 1 is the maximum eigenvalue of capital lambda. Actually, capital lambda is the diagonal matrix consists of the eigenvalues of x transpose x. These are the eigenvalues of x transpose x, and then lambda 1 is the maximum eigenvalue. Then lambda k is the minimum eigenvalue of lambda. So, in the presence of multicollinearity, lambda k is very small in comparison to lambda 1. So, kappa x is a measure of sensitivity of B, the OLS estimator. This B is your OLS estimator to changes in x transpose y or x transpose x. How much sensitive your OLS estimator is. Practice a condition number around 5 to 10. This represents weak dependence or weak multicollinearity, but a condition number around 30 to 100, this implies strong relations or strong multicollinearity. Next measure of multicollinearity is multicollinearity index. Multicollinearity index or MCI is defined as MCI equal to summation j equal to 1 to k lambda k upon lambda j whole square. So, we take the ratio of smallest eigenvalue and all the eigenvalues. So, jth eigenvalue is lambda j. So, we take lambda k upon lambda j, then we take square of this and then we take summation over j. Then MCI approximately equal to 1 indicates. So, in fact, here you are taking lambda k in the numerator. So, if there is multicollinearity, then the value of MCI will be small. In fact, a value of MCI around 1 indicates high multicollinearity and a value of MCI greater than 2 indicates little or no multicollinearity. Then the next measure is variance decomposition proportions. Now, the spectral decomposition of X transpose X is, say you can write X transpose X as summation I equal to 1 to k lambda I pi transpose. So, you can write the inverse of X transpose X as summation I equal to 1 to k 1 upon lambda I pi transpose. Now, suppose P L I square is the lth diagonal element of pi transpose. Then summation I equal to 1 to k P L I square upon lambda I is the lth diagonal element of X transpose X inverse. And then the variance of B L, the lth component of B is sigma square u summation I equal to 1 to k P L I square upon lambda I. And then we define the proportion of variance of B L associated with lambda I as phi L I equal to P L I square upon lambda I divided by summation j equal to 1 to k P L j square upon lambda j. Say this is the total variance of B L, the lth component of B. And then this has various components, say the variance associated with first eigenvalue lambda 1 is P L 1 square upon lambda 1. Variance associated with lambda 2 is P L 2 square upon lambda 2 and so on. So, the variance associated with lambda I is P L I square upon lambda I. So, this is the variance associated with eigenvalue lambda I and we divide it by the total variance summation j equal to 1 to k P L j square upon lambda j. So, finally, phi L I gives you the proportion of variance of B L associated with lambda I. Now, we form this table of variance decomposition proportions. So, suppose these are your eigenvalues lambda 1, lambda 2, so on lambda k. Then variance of B 1, variance of B 2, so on variance of B k we take towards this side. Now, the proportion of variance of B 1 associated with lambda 1 is phi 1 1, that associated with B 2 and lambda 1 is phi 2 1 and so on. The proportion of variance of B k associated with lambda 1 is phi k 1 and so on. Obviously, the sum of diagonal elements is equal to 1. If you take summation j equal to 1 to k phi j j, then this is equal to 1. This you can easily verify from here. If you take L equal to I, then we take summation over all I and then we get 1. Now, 2 or more large values of phi L j in a row indicate that multicollinearity is adversely affecting the precision of estimate of the associated coefficient. So, if we consider any particular row, suppose we consider this row. Now, suppose you have 2 or more large values of phi L j in this row, then this indicates that multicollinearity is adversely affecting the precision of estimate because of this eigen value. Next measure is variance inflation factor VIF. Now, suppose we run the regression between the jth regressor say x j and the remaining k minus 1 regressors say x 1 so on x j minus 1, x j plus 1 so on x k, and then R j square is the multiple correlation coefficient. If we run the regression, then VIF is defined as VIFJ equal to 1 upon 1 minus R j square. Now, VIF of 1 means there is no correlation. When this VIFJ becomes 1, when R j square is equal to 0. So, it means x j is not at all correlated with the other regressors x 1, x 2, x j minus 1, x j plus 1 so on x k. So, there is no correlation between the jth predictor and the remaining predictors. Then VIFs exceeding 4 warrant further investigation. So, VIF exceeding 4 means R j square is a bit small, means it is greater than 4. So, 1 minus R j square is less than 1 upon 4, or R j square is greater than 3 by 4 or 0.75. So, it is bit high. So, VIFs exceeding 4 warrant further investigation. Then VIFs exceeding 10 are signs of serious multicollinearity. When we get VIFs exceeding 10, when 1 minus R j square is less than 1 upon 10, or R j square is greater than 9 by 10, that is 0.9. So, it is quite high. So, then it is a sign of serious multicollinearity, means x j is highly correlated with all other predictors. So, you are facing the problem of multicollinearity here. Now, we consider solutions to multicollinearity problem. The first possible solution is additional observations. So, suppose x transpose x has a small root lambda corresponding to eigenvector p. Then suppose you take an additional observation y n plus 1, say corresponding to x n plus 1 equal to L p. So, you take x n plus 1 equal to L into p, where this L is some scalar, and then corresponding to this x n plus 1 you observe y n plus 1. Now, of course, in some experiments it may be possible for you to set the values of x's. So, you just set x n plus 1 equal to some constant time p. Then the model for complete set of observations is y n plus 1 equal to x n plus 1 transpose beta plus u, or y star equal to x star beta plus u. Now, we apply OLS to this model. Now, if you take x star transpose x star, then this is equal to x transpose x plus x n plus 1 x n plus 1 transpose. Therefore, x star transpose x star p is equal to x transpose x plus x n plus 1 x n plus 1 transpose p, or we take x n plus 1 equal to L p. So, you obtain x transpose x plus L p into L p transpose, or L square p p transpose into p. Then x transpose x p is equal to lambda p, because lambda is the eigenvalue of x transpose x corresponding to the eigenvector p. Further, in the second term, p transpose p is equal to 1. So, you get L square here into p. So, we can write it as lambda plus L square into p. Now, p is then eigenvector of x star transpose x star corresponding to the eigenvalue lambda plus L square. Now, remember why we were facing the multicollinearity problem, because lambda was small. You have a small eigenvalue, and then you are facing the problem of multicollinearity. But then corresponding to the new design matrix x star, the eigenvalue corresponding to the eigenvector p of x star transpose x star is lambda plus L square. So, it is greater than lambda, it has increased the value of lambda. So, it may resolve the problem of multicollinearity. So, choosing an additional observation in the direction of p can improve the precision of the estimator. Of course, it may not always be possible for you to choose an observation in the direction of p, but if it is possible, this is one of the possibility to resolve the multicollinearity issue. Now, some other methods to overcome multicollinearity problem are exact linear constraint, which leads to restricted regression estimator. So, if you have some information like this about beta, you can utilize this information, and then you develop restricted regression estimator, which resolves the problem of multicollinearity. Because if you look at the expression for restricted regression estimator, it adds some quantity in x transpose x. So, it resolves the problem of multicollinearity or stochastic linear restrictions. So, you get mixed regression estimator. We also discussed mixed regression estimator in one of the lectures. Or if you have linear inequality restrictions, then you can write these linear inequality restrictions as stochastic linear restrictions, and then again you can apply mixed regression estimator for estimating beta. This may resolve your problem. Now, we consider principal component regression method. So, we have the model y equal to x beta plus u. Then suppose p, which is equal to p 1 p 2 p k, is k by k matrix of orthogonal eigenvectors of x transpose x. Each of these p i's, say p 1, p 2, p k, these are k cross 1 vectors, k cross 1 orthogonal eigenvectors of x transpose x. Then suppose z I is equal to x p I is the ith principal component. Then z I transpose z I is equal to lambda I, because z I transpose z I is equal to p I transpose x transpose x p I. Now, x transpose x p I is equal to lambda I p I. So, you get lambda I p I transpose p I, and then p I transpose p I is equal to 1. So, you get lambda I, where lambda is the ith largest eigenvalue of x transpose x. Then this capital Z is equal to x p. So, obviously, capital Z is equal to Z 1, Z 2, Z k, and this is n cross k matrix of principal components. Each of these Z i's is of order n cross 1. So, capital Z is of order n cross k. Now, we can write the model as y equal to x p p transpose beta plus u, because p transpose is equal to identity matrix. And then we can write it as x p is equal to z, and then we write p transpose beta equal to theta. So, the model becomes y equal to z theta plus u. Now, these are the steps for obtaining the principal component estimator. We first delete some of the principal components Z i's corresponding to small eigenvalues. So, we select few smallest eigenvalues and then we delete the corresponding principal components Z i's. Now, we partition Z as x p 1 p 2 equal to say Z 1 Z 2. Then Z 1 is the matrix of principal components to be retained, and Z 2 is the matrix of principal components to be deleted. You want to delete these principal components. Now, Z 1 and Z 2 are orthogonal to each other, because you can easily verify that Z I transpose Z j for I not equal to j is equal to 0. Actually, Z I is equal to x transpose x p I. So, you get p I transpose x transpose x, then Z j is x transpose x p j. Then x transpose x p j is equal to lambda j, you get p j here, and then p I transpose x is equal to lambda I p I transpose. So, you get lambda I lambda j p I transpose p j, then p I transpose p j is equal to 0. So, you get 0. So, that is why Z 1 and Z 2 are orthogonal to each other. Now, we write the model 6 as y equal to Z 1 theta 1 plus Z 2 theta 2 plus u. Then the OLS estimator of theta 1 is theta 1 hat equal to Z 1 transpose Z 1 inverse Z 1 transpose y, and it has the covariance matrix sigma square u Z 1 transpose Z 1 inverse. Then we have beta equal to p theta. Actually, we have defined theta here. Theta is equal to p transpose beta. So, beta is equal to p theta. P is an orthogonal matrix, and then you can write it as p 1 theta 1 plus p 2 theta 2. Now, omitting the components of Z 2 means you are setting theta 2 equal to 0. Hence, the principal component estimator of beta is say beta hat equal to p 1 theta 1 hat, and theta 1 hat you have already obtained. This is equal to Z 1 transpose Z 1 inverse Z 1 transpose y, and then we write it as p theta hat star, where theta hat star is equal to say theta 1 hat transpose 0 transpose whole transpose, means theta hat star is like this, say theta 1 hat and 0. So, you can get this principal component estimator of beta. This principal component estimator has lower variance than OLS estimator, but it is biased unless the restriction p 2 theta 2 equal to 0 is satisfied. So, again I repeat the steps of the principal component estimator. First we transform the model as y equal to z theta plus u, and then we write it as z 1 theta 1 plus z 2 theta 2 plus u, and z 2 is the matrix of principal components which you want to delete. Now, z 1 and z 2 are orthogonal to each other. So, you can easily verify that the OLS estimator of theta 1 is theta 1 head equal to z 1 transpose z 1 inverse z 1 transpose y. So, we obtain the OLS estimator of theta 1. Then you have beta equal to p theta. You write it as p 1 theta 1 plus p 2 theta 2, and you want to omit the components z 2. It means, you set theta 2 equal to 0 here, and then beta head, which is the principal component estimator of beta, is equal to p 1 theta 1 head, and then you can write it as p theta head star, where theta head star is equal to the vector theta 1 head 0. So, actually what we have done, the OLS estimator has large variance, and OLS estimator is best in the class of all linear unbiased estimators. So, even the best linear unbiased estimator is not working well. So, we are moving to the class of biased estimators. Principal component estimator is a biased estimator, and it has lower variance than the OLS estimator, but it is biased. But it reduces the variance so much, the variance of OLS estimator so much, that the ultimate mean squared error, which is the sum of variance plus bias into bias transpose, is lower than the variance of OLS estimator. So, although you are moving away from the class of unbiased estimators to the class of biased estimators, the mean squared error of this estimator, principal component estimator, if it is lower than the variance of OLS estimator, then you get a better estimator. Again, the problem is how to select number of principal components to be omitted. So, for that purpose you can use the scree plot. So, a scree plot shows the eigenvalues in decreasing order. You take j on the x axis and the corresponding eigenvalues on the y axis, and you start from the largest eigenvalue. So, suppose we order the eigenvalues in decreasing order. So, first eigenvalue is the largest one, then you have the second largest eigenvalue, third largest, and so on. So, we plot the eigenvalues in decreasing order, and we assume that lambda 1 is greater than or equal to lambda 2, so on greater than or equal to lambda k. Without loss of generality, you can assume that the eigenvalues are in decreasing order. So, we are plotting lambda j's against j, and then we select the index of the last component before the plot flattens. So, in this graph you observe that after this point the plot almost flattens. So, you can retain first 5 principal components, and then you can omit the remaining principal components. Another option to select the number of principal components is variance explained criteria. Again we assume that the eigenvalues are in decreasing order. So, lambda 1 is greater than or equal to lambda 2, so on greater than or equal to lambda k. Then the trace of covariance matrix with j components deleted is sigma square u summation I equal to 1 to k minus j lambda I inverse. Remember that the variance of the ith component is sigma square u upon lambda I. So, if you retain just k minus j principal components and if you omit the last j components, then the trace of covariance matrix is this sigma square u summation I equal to 1 to k minus j lambda I inverse. Then percent reduction in trace of covariance matrix obtained from using a least square estimator with j independent linear restrictions is V j equal to summation I equal to k minus j plus 1 to k lambda I inverse divided by summation I equal to 1 to k lambda I inverse. So, this is the overall variance. This is the variance of the components which we have retained, and then the reduction in variance is equal to this part minus this part, and then sigma square u will cancel out, and if you subtract summation I equal to 1 to k lambda I inverse minus summation I equal to 1 to k minus j lambda I inverse, then you obtain summation I equal to k minus j plus 1 to k lambda I inverse, and this is the percentage reduction V j. So, V j is called the benchmark function of PC regression. Then total percent variation that is explained by the first k minus j loadings is summation I equal to 1 to k minus j lambda I inverse upon summation I equal to 1 to k lambda I inverse into 100. So, this is the percentage of variation explained by k minus j principal components or k minus j loadings. Then we may select j so that the above percentage explained by variation is more than say 80%. So, this is a rough rule. If this quantity is more than 80%, then now we consider ordinary ridge regression estimator. This estimator was proposed by Hoyle and Kennard in 1970. They published 2 papers in Technometrics. So, the estimator is defined as B star C equal to x transpose x plus k I inverse x transpose y, where C is greater than 0. So, in fact, the estimator adds a constant C in the diagonal elements of x transpose x. For C equal to 0, we get the OLS estimator B. Again, if you take expectation of B transpose B, then B transpose B has expectation beta transpose beta plus variance trace of variance covariance matrix of B, that is sigma square u trace of x transpose x inverse. Now, this is greater than beta transpose beta plus sigma square u upon lambda k. Lambda k is the smallest eigenvalue of x transpose x. Actually, what is trace of x transpose x inverse? This is equal to summation I equal to 1 to k 1 upon lambda I. So, obviously, this is greater than 1 upon lambda k. So, lambda k is the minimum eigenvalue of x transpose x. Then, for the small lambda k, squared length of OLS estimator is much larger than the square length of coefficient vector beta. This expectation is much larger than beta transpose beta if lambda k is small. So, that is why the OLS estimator becomes large in magnitude, and this is just because of this smallest eigenvalue lambda k. And since in the estimator we are adding a constant in the diagonal elements, we are defining ordinary ridge regression estimator by adding a constant in the diagonal elements of x transpose x. So, definitely it will increase the value of the smallest eigenvalue. So, we expect that it will improve the performance of the OLS estimator in the sense that the resulting estimator will be smaller in magnitude. Now, we obtain the bias and MSE of ordinary ridge regression estimator B star C. The bias of B star C is expectation of B star C minus beta equal to minus C x transpose x plus C I inverse beta, and the MSE matrix of B star C is equal to sigma square u x transpose x plus C I inverse x transpose x transpose x plus C I inverse, and then you have the second part C square x transpose x plus C I inverse beta beta transpose x plus C I inverse. So, now we prove these results. So, we observe that B star C is equal to x transpose x plus C I inverse x transpose y, and then you can write it as x transpose x plus C I inverse x transpose x b, and again we write it as x transpose x plus C I inverse x transpose x plus C I minus C I b. So, you obtain B minus C times x transpose x plus C I inverse B. Now, we take expectation. So, expectation of B star C is equal to, you get beta here minus C x transpose x plus C I inverse beta, or you obtain expectation of B star C minus beta equal to this quantity. So, we get this result. Now, we have to obtain the MSE matrix of B star C. So, first we obtain the variance covariance matrix of B star C, and for that purpose B star C minus expected value of B star C is equal to x transpose x plus C I inverse, then you have x transpose x b minus beta. So, expectation of B star C minus expectation of B star C, and then we take transpose of this, is equal to x transpose x plus C I inverse. Then you have x transpose x b minus beta transpose, and then x transpose x, again you have x transpose x plus C I inverse, and then we take expectation of this, and then we take expectation of b minus beta transpose, which is equal to sigma square u, and you get x transpose x plus C I whole inverse, and then x transpose x inverse x transpose x is equal to x transpose x. Again you have x transpose x plus C I inverse. So, this is the variance covariance matrix of B star C, and then MSE matrix of B star C is equal to, say suppose we denote it by V B star C. So, this is equal to V B star C plus bias B star C into bias B star C transpose. So, when we substitute the values of variance covariance matrix and bias here, we get this expression for the MSC matrix of B star C. Then mean squared error of ordinary ridge regression estimator is given by expectation of B star C minus beta transpose B star C minus beta. To obtain this expression, you simply take the trace of MSC matrix of B star C. So, the trace of first term is equal to sigma square u summation I equal to 1 to k lambda I upon lambda I plus C square. And then you have the second term. The trace of second term is C square beta transpose x plus C I in to the power minus 2 beta. So, this result I am leaving for you as an exercise. Then next problem is how to select C. So, first we discuss the ridge trace procedure. Ridge trace is a two-dimensional plot of B I star C and residual sum of squares against C. And then we select that value of C for which the estimated coefficients stabilize with increasing C. Reasonable signs, coefficients, magnitudes, sum of squared residuals and maximum variance inflation factor, these are also checked. Now, we have taken an example, a numerical example in which we have 4 explanatory variables x 1, x 2, x 3, x 4, and then we have fitted the model using and we have estimated actually the regression parameters using the ridge estimator. We have plotted the ridge coefficients corresponding to different values of C. We have also plotted the variance inflation factor VIF trace corresponding to the biasing parameter C. So, from this graph you observe that the minimum of MSC you get for the biasing parameter equal to 0.012. In fact, after this point you observe that all the coefficients almost stabilize for C equal to 0.012. You also observe that around the same value of C, say somewhere here, the VIF also stabilizes. So, this is how you can select the value of C, the biasing parameter, using ridge trace plot and the VIF trace plot. So, in fact, in these graphs we observe that as C increases, the coefficients shrink towards 0. Say you observe from here, all the coefficients shrink towards 0 as C increases. Then VIF also decreases rapidly as C gets bigger than 0. So, as C moves away from 0, then VIF decreases very rapidly. And we choose the smallest value of C where the regression coefficients become stable in the ridge trace and the VIF values become sufficiently small. So, this is how you can select the value of C using the ridge trace plot and VIF plot. Again, I am not going into much details of these two criterion, but rich trace plot is one of the option which you can use for obtaining the value of C, operational value of C. Then some other operational choices of C are, the choice of C given by Hoyle, Kennard and Baldwin is K S square upon B transpose B. S square is the OLS estimator of sigma square u, and this is the expression for the S square. Or the choice given by Lawless and Wang is K S square upon B transpose X B. Now, we consider generalized ridge regression estimator. So, again we consider the model in canonical form. So, that Z transpose Z is equal to diagonal lambda 1, lambda 2, so on lambda k, and we write it equal to capital lambda. Again all these eigenvalues are in decreasing order. Then suppose C is a diagonal matrix C 1, C 2, C k. Then generalized ridge regression estimator of theta is defined as say theta hat r equal to lambda plus C inverse Z transpose y. Now, Z transpose y can be written as Z transpose Z, Z transpose Z inverse Z transpose y. So, Z transpose Z is equal to lambda, and this is your theta hat, the OLS estimator of theta. And since all these matrices are diagonal matrices, say the ith diagonal element of lambda plus C is lambda I plus C, and this capital lambda is lambda I. So, the ith component of theta hat r is given by theta hat r I equal to lambda I upon lambda I plus C I theta hat I. So, this estimator is called the generalized ridge regression estimator. In ordinary regression estimator, we are adding a constant C in each of the diagonal element. In generalized ridge regression estimator, we are adding different constants in different diagonal elements or in different lambda i's. Then the expressions for the bias and MSE of theta hat r I are given by say now the bias and MSE of theta hat r I are given by say expectation of theta hat r I minus theta I equal to minus C I upon lambda I plus C I theta I, and expectation of theta hat r I minus theta I whole square is equal to lambda I sigma square u plus C I square theta I square upon lambda I plus C I whole square. And then the MSE of theta hat r I is minimum when C I is equal to sigma square u upon theta I square. Now, we prove this result. So, to prove this result, we write theta hat r I as say this is actually equal to lambda I upon lambda I plus C I theta I hat, and then in the numerator we add C I, we subtract C I. So, we obtain theta I hat minus C I upon lambda I plus C I theta I hat. So, expectation of theta hat r I is equal to theta I minus C I upon lambda I plus C I theta I. Expectation of theta I hat is equal to theta I. So, this term gives you the bias of ordinary ridge regression estimator theta hat r I. Further, to obtain the mean squared error, we write theta hat r I minus theta I as say lambda I upon lambda I plus C I theta hat I minus theta I, and then since you have subtracted minus theta I here. So, we add lambda I upon lambda I plus C I theta I here, and then you have minus theta I. So, you obtain lambda I upon lambda I plus C I theta I head minus theta I minus C I upon lambda I plus C I theta I. Now, we take square of this quantity and then we take expectation. So, you obtain this equal to lambda I square upon lambda I plus C I whole square, and then you have square of this term which has expectation sigma square u upon lambda I plus C I square upon lambda I plus C I whole square into theta I square. And then we have the cross product term. Cross product term has expectation 0, because this is a constant, and then expectation of theta I head minus theta I is equal to 0. And then if you simplify this summation, you get the expression for the MSC of theta head R I. To obtain the value of C I which minimizes this MSC, you simply differentiate it with respect to C I and then you solve it for C I. So, in fact, this value of C I which minimizes the MSC is not operational. So, to get an operational value of C I, usually we replace these parameters by their estimators, least square estimators. Then you get the operational ordinary rigid regression estimator. So, the multicollinearity problem actually severely affects the properties of OLS estimator. So, in this lecture we have discussed different measures for the detection of multicollinearity, and then obviously you require some alternative estimation procedures also to overcome the problem of multicollinearity. So, we have considered different estimation procedures, mainly one can go for the principal component estimator or ridge regression estimator to overcome the problem of multicollinearity. In ridge regression estimator, we have also discussed different operational values of selecting the value of biasing parameter C. Say one can use the values suggested by Hildreth and Hawk, or there are some other values also which we have discussed in this lecture. And then one can use the ridge trace plot or VIF plot for selecting the value of C, the operational values of C. So, this is where I am going to stop. Thank you.
Hello everybody, welcome back, and here I am to give a preview, very short obviously, in the area of what we mean by operation research and optimizations. So, we know operation research and optimization is used generally where you have some resources and you want to utilize them in the best possible way considering what your main objective is. Now, if we stop here and go back in the past, so the obvious question comes, from where did this technique of operation research and optimization, which is an area of mathematical techniques, come into the existence. So, generally even though the work has started from areas of mathematics, economics, but generally it is considered that operation research and optimizations were very heavily used and it became popular during World War to in trying to schedule different resources, manpower, armaments, considering there were resource constraints, time constraints and space constraints and so on and so forth. Now, for the general public, it should be aware that we consider from the academic point of view, there are different people, very famous people who have worked, but George Danzig is considered the father who really proposed the technique of linear programming as a very nice tool, where you can use operation research techniques in order to optimize the resources which are there depending on different constraints which you have. And after that, things have really moved very fast, they have been developing throughout the world, they have been usage, they are different type of societies, so on and so forth. And in course of time we see and we still find exciting areas of application, but theoretically there has been a growth in techniques like robust optimization, stochastic optimization, dynamic programming, parametric programming, nonlinear programming, so on and so forth, and they are used depending on the concept and the areas of application which we see for either finance, for marketing, for scheduling, for engineering field and so on and so forth. Now, application of OR and optimization, if somebody asks, is a very difficult question to answer, because if I start now, it will almost take about 1 hour to give you all the areas of application of optimization operation research are. But to keep it very brief, considering that you are all ready and eager to take that as a subject, I will just highlight the areas of applications, some of which are in scheduling, in assignment problem, in facility location, like you want to build up a factory, you want to build up some storehouse, so on and so forth. It is used in network flows, like you want to transport some goods, transport manpower from one area to another area. So, how we will try to basically do it in the best possible way. What is best would obviously depend on how you are trying to use optimization as a tool in different areas. It can be used, operation research and optimization can be used in health services, in financial portfolio management, asset liability management, game theory and so on and so forth. Now, in the recent past, even though it is very well known, but still I would like to highlight the point that the computing powers and the techniques of operation research and obviously in statistics has exponentially grown. And with very sophisticated programming being available, like we know that there is MATLAB, there is R, there is SAS, which are different type of optimization tools. We see nowadays that operation research and optimization is also used in health sciences, in gene replication theory, in area of say for example prediction of weather, in the area of say for example prediction of earthquake, how you find out the best possible way to take actions such that it meets your overall demand. Say for example in prediction of earthquakes, you would like to basically build up your houses, build up the dams, build up the overall locations of people staying in different localities in such a way that the minimization of the losses are sustained. Furthermore, after the advent of computing and advent of different techniques, we see many meta heuristic and heuristic techniques are very heavily used in parlance of operation research and optimization by joining them together such that you get the best benefit. So, if the question arises what are the meta heuristic techniques, I would again be very brief, because again there is a huge amount of literature, huge amount of application areas, huge amount of research which are being done in the area of genetic algorithm, taboo search, ant colony optimization, simulated annealing, then in the area of particle swarm optimization, in the area of artificial immune system and so on and so forth. In the coming years, it is thought and definitely with some positive viewpoint that the area of multi-criteria decision making and multi-objective programming, where you use different type of tools and use the different advancement of optimization which has been made in such a way that you can basically optimize two different objective functions which are there in front of you, such that either if considering the area of finance, you can either maximize your return for the portfolio or minimize the risk also, or say for example you want to basically have a layout such that minimization of cost is one factor, and the maximization of, say for example, benefit which accrues to different type of users in this overall layout can be attained at the same time. So, obviously, it means that what we are seeing is a huge application of optimization along with different type of computing and heuristic techniques, such that in years to come this area of optimization would become one of the best tools where you accrue and get the benefits in the best possible way. And I am sure that the students or the participants who will take this course will find it an exciting add on to their CVs and to their curriculum vitae, such that they can understand the techniques, how they can be used in the best possible practical sense. Thank you.